Welcome to Chemistry 111. You're the teacher, Andrew Evans. We'll start today by looking at the tests. So we finished chapters 6, 7, and 8, which were essentially 6 was Lewis Structures. 7 was, then we went into VSEPR models and bonding theory. And 8 was all about chemical reactions and aqueous chemistry. So we'll go through 2 different tests, at least the relevant questions for 2 different tests. If we don't get it all done today, we'll continue it on Wednesday. But I will be going through these 2 tests before we even talk about the exam, which is probably going to send it to you pretty soon-ish. But it won't be due till probably Sunday evening right before mole week. We have mole day, 1023. You've learned about moles a little bit ago. 1023, that's 10 to the 23rd power. That's Avogadro's number, 6.02. Well, mole day is coming up, so there's going to be some incredibly nerdy stuff done by the chemistry club all that week. We're going to try to do some cool demos. We'll see what we can do. The theme of this year is sticking with chemistry, so we'll probably make a bunch of different slimes and goos and gack and whatnot for people to play with. So come on by. That in mind, let's go ahead and go straight to the... So this test was test 5 last year. Well, yeah, spring of 19. It was when the last 2-3 chapters were all about the Lewis orbitals. So obviously it's a different order, but we'll go through it. So draw the Lewis structure. So be prepared to draw Lewis structures. How will we do this online? Actually, I'm going to jump straight to that and discuss that. How we're going to do this online is we are going to do something like I have on this quiz right here. This quiz is for nursing chemistry. For a little quiz, draw the Lewis structure of this file. So what they would have to do is draw this, maybe take a picture of this, or somehow get this as a digital copy. And then as part of the test, you will upload that file. That is how we will do the Lewis structures. So be prepared for at least 3 or 4 of those. I'm going to give you an extra hour on the test so you can fiddle around with this in case I might just give you those questions separately. That way this won't be a hindrance. So I don't know how I'm going to exactly do it just yet, but needless to say, there will be something like this. So I might give you, here's just the Lewis test 3.1, where this is all the Lewis stuff, and test 3.2, which is everything else. But it's going to be something like that where you upload the files. And so you'll have to at least be able to do that. Okay. Back to this. So we want to draw the Lewis structure for Cl(O3)1-. If I'm reading that right. I could be, my eyes could be shot and because these are really tiny print. But Cl(O3)1-. Yes. So what we want to do, always when we're doing these drawings, we want to show all the lone pairs, count all the things, make sure we get them right. So Cl(O3)1-, that's maybe a little bit too, let's see blue. Yeah, well, this might be a little bit better, I don't know. But Cl has 7. Each oxygen has 6. There's 3 oxygen, so it's 18. And because it's 1 minus, we have to add another electron. So 18 plus 8 happens to be 26 electrons to deal with. We're going to take our first element in the series. That is probably going to be our center element. Cl. We're going to put single bonds to every element off of that, unless it's a bigger compound. So that uses up 6 electrons. We're down to 20. We are going to put a valence, we're going to put a octet level of electrons on all the chlorines, on all the oxygens. So that means since the oxygen has 1 bond, it needs 6 more electrons. So we're going to use 18 electrons. That leaves 2. The one thing we can't forget, put any remaining electrons on the center atom. Okay, now, since I don't say a Lewis structure with the lowest formal charge, that would be perfectly acceptable. What is the formal charge? Chlorine should have 7 electrons. It has 1, 2, 3, 4, 5. Formal charge of 2 plus. Each oxygen should have 6, and it actually has 1, 2, 3, 4, 5, 6, 7. So each oxygen has a formal charge of 1 minus. 3 negatives, 1 double positive adds up to total charge -1. However, we could lower the formal charge by making double bonds. Doesn't matter which double bonds? No. Just we could make it 2 double bonds and 1 single bond. And that would give it 0 formal charge, where it has this, well, this guy has 1 formal charge. 1, 2, 3, 4, 5, 6, 7. But now chlorine has 1, 2, 3, 4, 5, 6, 7. 0 formal charge on the chlorine. The oxygen now has 1, 2, 3, 4, 5, 6. So each oxygen, except for the last guy, has 0 formal charge. So either one of those structures would be technically accurate for just a valid Lewis structure. Okay, scrolling down. Skipping 2. 2 would be chapter 5 material. We don't need to worry about that. This is way harder than what you're going to see on the test, but the basic structure here, this is ATP, for one of the molecule energies of life that you need to know for what biology. But what this asks is, what is the hybridization of the following atoms? This looks incredibly hard, but really, you count the bonds, you count the single bonds, and that is going to be related to your hybridization. So I ask you, phosphorus number 1. What is the hybridization? Well, how many bonds does that phosphorus have to make? 1, 2, 3, 4. What would the hybridization be of phosphorus number 1? sp3. Carbon number 2. Carbon number 2 makes 1, 2, 3, 4. It would be sp3. Oxygen number 3. Part of the thing here is you have to recognize how many electrons should the guy have. This phosphorus should have 5. 1, 2, 3, 4, 5. So that's good. The carbon should have 4. 1, 2, 3, 4. That oxygen should have 6 electrons. 1, 2, 3, 4, 5, 6. There is 2 unseen lone pairs. 2 unseen lone pairs. One of the hints I gave them at the very beginning was, when in doubt, draw the structures including the lone pairs. Don't forget, some of these structures don't have the lone pairs drawn on them. So that guy, that oxygen, has 4 things coming off of it. 2 bonds, 2 lone pairs. It's also sp3. Let's see. This nitrogen, can't see, where's nitrogen number 4? N4s. I'm not sure if it's, there's carbon 5. This carbon 5, I'm going to skip to carbon 5 until I can find nitrogen 4. 1, 2, 3 things coming off, so that'd be sp2. And then finally, oh, N4 is up at the top. I can't really see that. Nitrogen should have 5 electrons. So there is one lone pair coming off of this nitrogen. That is sp2. So the answer again was sp3, 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 sp2, sp2. If you had done this guy without drawing in the lone pairs, you would have said this oxygen is sp and that nitrogen is sp. So you got to make sure to put in the lone pairs if they're not already given. I think I've been a little bit nicer about this test, but keep in mind, hybridization is not hard if you remember this simple fact. We are looking at how many things are coming off the atom, and that has to do with the hybridization. 4 things coming off, sp3. So 1s and 3p add up to 4. Now, once again, this is a hard structure. N2O. This is a hard structure. I'm not giving you something so hard this time around. N2O. There's 2 N's, but only one N will be the center atom. So it's basically like NNO. This is what the structure looks like. So N2O, 5 times 2 is 10, plus 6 is 16. So N, O, that's 4 electrons. Put 1, 2, 3, 4, 5, 6. 1, 2, 6. There's all my electrons. Now, you have several structures you can draw. No matter what, that center nitrogen is not happy. The center nitrogen is not happy because it is 4 electrons shy of an octet. So what can we do to make that center nitrogen 2 double bonds? You could do it like this. Well, I'm going to do it. You could do it like this. You could do it like that. And you could do it like this. The bottom one is perhaps the least good one. But that's just because of formal charges. This one, remember, nitrogen wants to have 5 electrons. No matter what, this nitrogen is going to be +1 in all these structures because all these nitrogens have 4 things coming off of it. 4 electrons. So in this structure, 1, 2, 3, 4, 5. 0 on that guy. 1, 2, 3, 4, 5, 6, 7. With the formal charges on the oxygen. 1, 2, 3, 4, 5, 6. This one puts the formal charge on the nitrogen. This one puts a formal charge on the oxygen and 2 formal charges on that nitrogen. So, honestly, the top structure is the best structure, though this middle structure is semi-acceptable. In a rule for the best Lewis structure, we want to put the formal charge on the atom with the highest electronegativity, which happens to be oxygen. So given the choice of putting a negative on oxygen or a negative on nitrogen, we'd much rather put a negative on oxygen. But I would have willingly accepted either of those structures, as long as I say, do a valid. Draw a Lewis structure for laughing gas with nitrogen as the central hydrogen. I don't say draw the best Lewis structure. So, that in mind. Once again, this structure is maybe a little bit harder than we have. What you have to do here, put in any lone pairs, continue all. I've made this a little bit harder, but I've fixed this to make this a little bit easier. One thing you have to keep in mind is when this says CH3 or OH or anything like that, what that is saying is that that's a C with 3 CH bonds coming off of it. But for sigma and pi bonds, this one, if you know it, it's so easy. If you don't know what the hell I'm talking about, you're out of luck. There's no way you can like multiple guess that. Sigma bonds, you count all the bonds once. All the bonds once. Once you've done that, that is your number of sigma bonds. On here, the shown bonds. Let's look at the shown bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we have the understood bonds, which is the CHs. So there is 3 CH3s, meaning there is extra 9 bonds not shown. The CH3s, we're saying a CH3 is equivalent to a CHHH. So the total number of bonds, of sigma bonds, is 16 plus 9, or 25. Now the pi bonds, every single double bond, or you count a triple bond twice, but every single double bond is a pi bond. So you have a pi from the CO, a pi from the CN, another pi from the CO, and then a pi from the CC. So 4 pi bonds. So I had the 1, 2, 3, 4. So 25 sigma, 4 pi. And that would be for that molecule. Expect an easier model completely drawn out for the test. I did my best to try to make this as simple as possible. So if you know it, you get it. You get the points. And I'm not trying to trip you up, because oftentimes I'd make a big molecule because if you know it, I want to make it semi-challenging. But people would always miscount something and they'd lose some points because instead of 25, they'd get 24 somehow. They would miss a bond. So I'm trying to make that less likely to miss it. If it's completely spelled out and all the bonds are shown, just number the bonds. Just number the bonds, it will help you. But okay, this one is a good question to ask. It's a little tricky if you understand if you don't understand it, but it's not too bad. Given this structure, PCl3F2, draw a polar and a nonpolar version. So the difference between this, when you have a molecule that has the same electron geometry as it does the molecular geometry. So this guy's going to be trigonal bipyramidal. Trigonal bipyramidal. There is a rule that essentially says if all the atoms are opposite, they cancel out. If the atoms are not opposite, it can very well be polar. So for the generalized structure of P, wedge, the two possibilities are the nonpolar one has all three chlorines right here and the F's on top. There's only one possible answer for the nonpolar because it has to have those two F's on opposite sides. On no other structure are those F's on opposite sides. So this is the nonpolar structure. For the polar structure, you basically have to mix up any of the F's. You could put an F here and an F anywhere on the wheel. Or you could put both F's on the equator of that. Because these three atoms are not equal and opposite, they do not cancel out. These two are equal and opposite, but you have to consider all three. You have to consider all three. So either of these two structures would have been valid for the polar structure. So whenever the electron geometry and the molecular geometry are the same, you're looking polar is equal and opposite. Polar is equal and not equal and opposite. Nonpolar would be equal and opposite. So F is opposite of F. These three CLs are all in the same. Now, there are several other structures where that could play a part. Questions like octahedral geometry, that's a common one. But so is square planar. Square planar, the electronic geometry and the molecular geometry do not match. But there's the perfect option of being equal and opposite, because it could be on opposite ends of the square. So we can skip this one. This one was for a different chapter. We don't while I went over this in class, I'm not actually going to ask you that on the test. So there's actually, the only math you might even be asked would be determining if something is polar or not by comparing two electronegativity values. So there's actually going to be like zero need for a real calculator for this test. So lysergic acid. Once again, what is the hybridization of these numbered atoms? You don't know, lysergic acid diethylamide is LSD. But basically coming off of here, see, atom 1, CH, CC, C double bond, C. There's 1, 2, 3 things coming off. It's sp2. 1, 2, there's carbon 2. 1, 2, 3, 4. That's a CH2. There's 2 H's coming off of there. 1, 2, 3, 4. sp3. That's a carbon. 1, 2. So 1, 2, 3, that's sp2. Let's see. Where's 4? Oh, there we go. 1, 2, 3, 4. Let's say 1, 2, 3, and there's a lone pair on the nitrogen that you do not see. The sp3, 1, 2, 3, lone pair on the nitrogen, sp3. Most of these structures, that if you get something like this, it will probably be sp3 or sp2. There's rarely will we see a big structure that goes beyond sp3. Look at this. Structures contain a molecular dipole. Once again, equal and opposite, equal and opposite, equal and opposite. This is a perfectly reasonable question. This guy, if I'm not mistaken, F, 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 H. Well, these F's are canceling each other out. This H is different. This F and this H do not cancel each other out, so that could be polar. ClF, ClF, FCl. These guys are not canceling each other out. That guy's polar. Here's the FFF. Those guys cancel each other out. ClCl, those guys cancel each other out. That guy is nonpolar. And this guy, it's tetrahedral. They're all Fs. Even though it doesn't look it, that guy is nonpolar. The correct answer is 1 and 2. So look at your lab stuff. Look at your lab stuff. If you get your lab stuff into me, I can grade it, and you can kind of see what we should be doing. But that guy, the electronic geometry and the molecular geometry are the same, and all the atoms are the same. So by definition, it is going to be nonpolar. Skipping. Okay. Be prepared for questions like this. What is the electron domain geometry of this? You have to draw this out on your own and then determine that. Electron domain geometry or electronic geometry is the one that just looks at the base geometry, not the shape where we differentiate the lone pairs from the bonds. But you have to draw this out. You don't have to draw it out on the sheet, but you might need some scratch paper to draw this out. Expect a couple of them like this. So, ASO3, is that 1 minus? ASO3, 1 minus. So, to do this, the beauty of this is it doesn't matter whether you do high formal charge or low formal charge. ASO3, 1 minus. Arsenic is under nitrogen, under phosphorus. It is 5. Oxygen, 3 plus 1. 18 plus 16, 24. 18 plus 6, sorry, 24. Okay, AS in the center. Single bond, single bond, single bond. That's 6 electrons. We're down to 18. 2, 4, 6, 1, 6, 4, 6. That's all the electrons. To make arsenic happy, we would make at least 1 double bond. Now, how many things are coming off the arsenic? 1, 2, 3. What's its shape? Going to be trigonal planar. Now, this structure has formal charge, 3 formal charges. Had I drawn a structure with an expanded octet so that there's only 1 formal charge, how many things are coming off the arsenic? 2, 3. Still 3, still trigonal planar. So it doesn't matter whether you do high formal charge or low formal charge, you will get the same structure. And it'll still be trigonal planar as your answer. So that's what I'm trying to say. As long as you follow the rules, you should be in luck. It'd be trigonal planar. If you just guessed, you might say, oh, arsenic has 5 electrons, there's 3 things coming off. Put a lone pair, it's trigonal pyramidal. Or there's 3 things coming off, maybe it's T-shaped. It looks like a big thing. And so you want to draw it. You want to draw it. You usually want to draw this guy. Draw the Lewis structure of the sulfur trioxide. So SO3. And then xenon tetrabromide. So I'll do those 2 real quick. So, but I wanted to pull those up so I can do them back to back. So Lewis structures. Even if I'm not requiring you to actually draw the Lewis structures, because there's only like, I think 3 maybe actual drawings, maybe 4 that you'll have to do. You're still going to have to be able to draw them out if you want to figure out electronic geometry. So SO3 and xenon tetrabromide. So S, 6. Oxygen, that's another 6 times 3, that's 18, 24. S, I'm blessed with the fact that the one we just did was almost identical. That would be an acceptable structure. A better structure might be this. Even better structure might be this. But it doesn't matter. Right now, you could draw 3 double bonds to the sulfur so everyone has 0 formal charge. Or you could draw like 1 double bond. Either way gets you octet or expanded octet on everything. Xenon, that's 8. Bromine, there's 7 per bromine. Sometimes 4, that's 28. So 28 plus 8 is 36. Xenon, bromine, 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 bromine. 1, 2, 3. Sorry, that's 8, which knocks it down to 28. Then I put 6 on everything. That knocks out 24. So we're down to 4. We put 2 lone pairs on xenon. If we were to ask something about its electronic geometry, you would say it is octahedral. If you were to be asked anything about what is its molecular geometry, you would say it's square planar. But I'm only asking you to draw a Lewis structure. It doesn't have to be pretty like that one. It would just have to be a Lewis structure. Okay, let's see which. It stays atoms true. I don't think, yeah, that's not for this test. Molecular geometry of chlorine trifluoride. Yeah. Chlorine trifluoride. What is it? Yeah. This one, you draw this guy out. You draw this guy out. You would get I'll go ahead and do it. I don't really want to do it. I'm getting tired, but we'll do it. I made them do it last year. I'll do it. Oh, okay. Okay. Yeah, you could. Yeah. Well, draw along with me. So Cl F3. We have Cl has 7 electrons. Fluorine also has 7 electrons. We're going to have, 28 electrons to deal with. We put on chlorine in the center. We use 6 electrons to make our 3 bonds. 28 minus 6 is 22. Each fluorine needs 6 electrons. So we're going to use 18. That knocks it down to 4, which means we have 1, 2, 3, 4. So with that in mind, we have our Lewis structure. This one I think was on the lab. But 1, 2, 3, 4, 5 electron domains. So, yeah, trigonal pyramidal. How many of them are lone pairs? 2. So that means we move 2 steps to the right and put it to T shape. And so if you have that sheet in front of you while you're doing the test, you're drawing this out, you're working this out, you're given a serious advantage. So what is a molecular geometry? Okay, so this one is something I might ask of you. What is the molecular geometry of these atoms? This one was a multiple choice, but literally what it comes down to, it's the same thing as the hybridization. Put in the lone pairs, count the electron domains, count how many of them are lone pairs. So carbon number 1, I can find where carbon number 1 is. Carbon number 1 is there, I think. 1, 2, 3, 4. Carbon is expected to have 4 bonds. It is tetrahedral. Let's see. Nitrogen number 2. Atom number 2. Let's see. Is that? Is that? Yeah, that looks like 2. Now, connected to an H, and it's connected to 2 carbons, and nitrogen should have 5. 1, 2, 3, 4, 5. A lone pair. That is trigonal pyramidal. Okay. So the thing here, we're looking at this structure. We're looking at wedge dash H for nitrogen. Nitrogen should have 5 valence electrons. How many electrons does it need to have an octet? And how many do you see right there? 2, 4, 6. So what does that mean? It is missing all the atoms in this structure should have an octet. So if they don't have an octet, there's a lone pair that is not shown. As I said, I tried to make the lone pairs abundantly clear. I tried to put in the lone pairs into the structures. So this won't be as big of an issue. But when we look at these, almost all the structures should have an octet or an expanded octet. So if you do not see the octet, it is missing a lone pair. So in this case, that nitrogen would be trigonal pyramidal because of that lone pair. The next atom, carbon 3. Is that carbon 3? Yeah. Okay, so 1, 2, 3, as 2, 4, 6, 8. That's going to be trigonal planar. And then, yeah, so we want the tetrahedral, trigonal pyramidal, trigonal planar. As I said, this structure is much harder than I tried to do on the test. That's amoxicillin, a common antibiotic. See, and then there's electron geometry, and then draw these two resonance structures. Be able to recognize resonance structures. Be able to recognize resonance structures. We've done this one in class. I'm going to skip this one, but SCN, the C is in the center. You have S on one side, N on the other. You could have a single bond between S and C, a triple bond between C and N. You could have a double bond between S and C, a double bond between C and N, and a triple bond between S and C, and a single bond between C and N. Those are all resonance structures. You keep the sigma bonds, you move the pi bonds around. So whenever there's double bonds, so S, so you're leaving this base structure intact. Over here. You're leaving this base structure intact, the S and that base structure intact, and what they're putting double bond, or your triple bond. Basically, to get from here to here, you're essentially taking this and like swinging like a door on a hinge over to there. Or you could draw that going over to there. And so you could have that structure. And those are resonance structures. Resonance structures are when the double bonds can flip to the flop, and get from one place to the other. So recognize this guy would not be a resonance structure because this is a completely different like combination of the atoms. But this one, because the double bonds have moved around. The example I will give you real quick in the that was in your lab is O3. You could have that structure, but you could also draw that structure. The double bond has essentially flipped from there to there. And the extra credit for that one, which will be next test extra credit, is seriously just, if I were to teach us next year, which I probably will, what would you have me do differently? And obviously you can't be like, well, don't teach it online. It's like, well, I can't really help that. Can't really help that. Okay, but this is garbage. We don't need, this is goofed up, but you will have this table. I gotta bring to the front. Yeah. Let's just delete that one. That's easy enough. Okay, or not. Come on, delete. Yeah. There we go. I just wanted to show. So you will have this Pauling electronegativity table already attached to your test. Whether you need it or not, it's kind of up to you. But I included that as well as this and the solubility table. Now, that's as far as we will go for today. There was a lot of stuff going on. Come Wednesday, we will look at the stuff relating to Chapter 8. So how will you see questions relating to net ionic equation and I'll try to show you how you should type it in. But keep in mind, as you type it in on the test, I will still go through it. So if you type something in wrong that it makes the thing unhappy with you and marks it wrong, I give you points back, as long as it's not egregious. Like if I want you to type a caret to show a superscript and you type, I don't know, something else, you hit the wrong key. As long as it's like, well, I can clearly see you meant to type a key to show this as a superscript, you'll get points. But okay, that is as far as we'll go, mainly because we got 5 minutes left. It's not worth pulling up the next test right this second. But as I said, test will probably be due on Sunday. In the meantime, Andrew Evans, have a good day.